Electric charge. Electric charge is the physical property of matter that causes charged objects to experience an electric force. Two objects that have an excess of one type of charge will exert an electric force on each other when relatively close together. In other words, if I have a positively charged object, that implies that there are less electrons. On the other hand, if I have a negatively charged object, that implies that there are more electrons. So for attractive, no, let's say for electric forces to occur, if I have a positive charge, now remember what that means then. So when I look at this, what this means here is that there are less electrons, right? That means less electrons. There's still electrons there. They're the inner electrons, as we'll talk about. And if I have a negatively charged object, that means that they have more electrons. So if this is the case, then they will feel an attractive force between them. On the other hand, imagine that I have spheres that have more electrons in each situation. So what we're going to see here is that now there is a repulsive force because each of these objects has more negative charge. So let's define a couple of things. Let's talk about the units of charge. Both the electron and proton have equal but opposite sign charge. And our unit of charge, so that what we say here is that our unit of charge is defined as 1e. So that means here that if I have an electron charge, this will then equal minus 1e. If I have a proton charge, I'm going to have a positive 1e, where the ratio of these two charges, in other words, the ratio of the proton charge to the charge of an electron is almost exactly 1. So 1.000 plus or minus, let me be careful, plus or minus 10 to the minus 20. Now, this is a miraculous statement because the proton is a composite charge. The electron is not a composite charge. However, that's not the official unit. The official SI unit of charge is much larger, since measuring a single charge value is difficult. So the official unit of a charge is 1 coulomb, which is equal to 1C, which is equal to 6.25 times 10 to the 18 electrons. Or it's typically written as 1e is equal to 1.602 times 10 to the negative 19 coulombs. This is the most common way that people write electric charge, just like that. One should treat this relation as a conversion factor. So, like for example, if I have one electric charge, that's the same as 1e times, and you could see that 1 coulomb, and if I'm going to convert this, I have to have electrons in the denominator, so this will be 6.25 times 10 to the 18 electric charges divided into 1 coulomb. And if you compute that, you get 1.602 times 10 to the negative 19 coulombs. That's what I mean by a conversion factor. The way a unit of coulomb of charge is derived by measuring the electric current accurately. So it makes sense in that context because it says this. So if I have a current, it's equal to dq dt, which is the same as 1 coulomb per second. That by definition is 1 amp of current. So if you can measure 1 amp of current very accurately, you know that there are 6.25 times 10 to the 8 electrons. That's how a coulomb is defined. Now that we've defined charge, I want to come back to the question that we had at the end of lecture 1.1. After our discussion of the electric force being much, much bigger than the gravitational force, this begs the following question. If electric forces are much stronger than G forces, gravitational forces, why don't we feel electric forces more in everyday situations? And that's a really good question. And it turns out that it's deep. So if I was to say this is the answer to that question, we say that atoms in general are extremely neutral to a high degree. This means that atoms are composed of equal number of protons and electrons. Because of this, the charge of an atom is then going to be the charge of a proton plus the charge of electrons. And because they're equal in number, they sum to 0. In other words, zero electric charge implies zero electric force. That's no surprise. So in general, most atoms are neutral to a high degree. I mean, there are ions, that means atoms or molecules that have lost charge. In other words, they either gained or lost electric charge in the Earth's atmosphere. There is because sunlight causes air molecules to break apart as UV light interacts with them. So, you'll hear some responses that a simple answer would also be that because of the largeness of the attractive electric force between the positive nucleus charge and electrons, that they're not easy to remove. So what I'm going to do is give you a more detailed answer that's at a higher level, but it will make more sense, hopefully. So here is a more detailed answer at a higher level. And it goes like this. The energy to remove an electron from an atom is called the ionization energy. But this goes from a lot. This goes by a lot of names. It could also be called the binding energy. So the work required to overcome the binding energy is the ionization. So sometimes you'll hear people say binding energy or ionization energy. They're one and the same. And it turns out that for atoms in general, so for atoms, if you can ionize them, for atoms, their values are between 5 and 10 electron volts. Now note that you shouldn't worry about the unit electron volt right now. It's just the standard unit that people look at light particles called photons have. But it's essentially how much energy can you add to an electron to ionize it from the atom. At visible, no, not at, visible light carries energies less than 3 electron volts and cannot ionize most free atoms. So think about that. So here on Earth, what we generally see is visible light. The energy required to ionize electrons from atoms is too high for visible light to actually do that. Like I said already, in the upper atmosphere, You can ionize atoms, and it happens all the time by UV light, coming in from the sun during the day and doing that. For typical temperatures on Earth, and so what we'll find here is that here's what you find. So if you look at typical temperatures, that's 300 K. So that's about, let's say, somewhere between 70 and 75 degrees Fahrenheit. And that carries an energy, and this is what this KBT means. This is essentially the energy at this temperature. This energy turns out to be about 1/40th of an electron, are too low to ionize atoms. That's the main reason why objects are neutral to a high degree. So once again, the relatively stability of atoms occurring is that stable atoms require more energy to ionize. That means to release their electrons. That's why there are few electrons in nature right there. So in other words, it's just that we live in a place where electron transfer is not common. Maybe I should say super common. If it was common, we would have a different perspective on chemistry. Okay? We would have the chemistry that we have today would be quite different. It's too often forgotten that our conceptual framework is shaped by Earth being in a certain temperature and pressure region. So, that being said, there are ions on the surface of Earth. Via charge transfer processes. In our first lab, one will be asked to estimate the number of electrons via charging by contact transferred to a balloon. So what you're going to do here is that you're going to rub a balloon on your head. And when you do that, we're going to ask you to find something that you can actually attach it to. And if you were in our lab, this would be wood or a whiteboard material. And what we would do here is that we would do this here. We're going to have a balloon. So when I'm looking at this balloon, it's a red balloon, let's say, and you're going to find out that there's going to be electrons that have been transferred. So what you're going to find here is that you have electrons transferred to a neutral balloon. Using Newton's second law, one will be asked to estimate the number of electrons by setting the net force equal to 0, where this now is then going to be the force of gravity minus the electric force between these two. So once again, one will be asked to estimate the number of electrons for F net equal to 0, which will then be the gravitational force minus the electric force. And when I draw a free body diagram, you're going to see that this will be the weight of paper clips, and the other force is going to be the force of the electrical force. So there's a balanced situation here. So the number is quite shocking. Okay. And this is what you're going to find. You're going to find that the number of extra electrons compared to the number of total electrons on the balloon is going to be of the order of about 1 to 10 to the 13. And you're going to see that, well, we'll talk about it more in class here, but that's about 1 in 10 to the 13. So to get a sense of charge and why charge is why the electric force is not really felt, our whole goal here is to get an understanding of what does 10 to the 1 part and 10 to the 13 mean. So the number 1 over 10 to the 13 is a minuscule number of electrons transferred compared to the number of electrons already on the balloon. And what you're going to find here is that there's about 1 billion electrons transferred. And that seems like that's a crazy number, 1 billion electrons. So to get a sense of this thing, we have to do some analogy. So let's think about an analogy here. The whole analogy is to get a feel for 1 over 10 to the 13, because that's an important number. All ordinary objects essentially are neutral to 1 part and 10 to the 13 electrons. So here's what we'll do. Let's compare a single drop of water versus the water level in an Olympic pool. So let's think about this. So imagine that I have a gallon of water. And by the way, we can easily estimate this. We're not going to do that, but you could imagine that I have a gallon of water. So in this situation, we're going to say that 1 gallon of water is about 100,000 drops. By the way, you can calculate this, or you can actually just Google it. I actually calculated it and I Googled it. So it depends on the size of the drops. Now, on the other hand, we have an Olympic pool. And of course, the Olympic pool is gigantic, right? We have a huge pool. So when I'm thinking about this Olympic pool here, we know that it's ginormous. So here I had to look this up, but here's what we find. An Olympic has 100,000 gallons. Well, I'm going to approximate that and say that that's about 10 to the 6 gallons, right? That's about a 1,000,000 gallons. And if you look at that, 1 gallon is about 10 to the 5. So then this would then be effectively 10 to the 11 drops of water. So remember, our whole goal is to get a feel for what is 1 and 10 to the 13th. Now, suppose you are hired to keep the water level in the Olympic pool to 100th of a drop. So let me make sure you're understanding what I'm saying here. So suppose you are hired to keep the water level in the Olympic pool to 100th of a drop. In other words, you are being paid, hopefully, a lot of money, and you have to keep the water level right here, right? So here's my water level. So you have to keep, so in here, there are 10 to the 11 drops of water in the pool. And right here, you have this crazy job that you have to keep the level to 100th the diameter of a single, here I got a single drop, right? Immediately you say that this is just crazy to ask somebody to keep the level to 100th the diameter of a single drop. I mean, that's insane. This is the meaning of the number 1 in 10 to the 13th. That's what that means. Now, transferring charge, excuse me, transferring charge, I'm going to say this differently. Now, transferring the meaning of neutralness in everyday materials, they are extremely neutral by 1 and 10 to the 13th. Therefore, objects in general will not experience an electrical force. That is why one does not feel strong electrical forces acting on you.